Hello, hi everyone. So this week we'll be discussing about local search and genetic algorithms. So till now whatever we have discussed, we have discussed about uninformed search. We said no, uninformed search doesn't seem uh, uh, realistic. We also can have some additional information. We are putting heuristics and extra information into the problem, and we're calling it as an informed search. Now this week we'll learn about local search, and also we'll think about the evolutionary algorithm, also known as genetic algorithms, and then we'll solve few problems related to these topics. So if you see, we started with there is something called satisfaction. Satisfaction means a function will be given and some set of constraints on those variables which involved in the function will be given, and you need to find out the satisfying condition, the domain of those variables. So goal satisfaction means reach the goal node, constraint satisfaction. While in optimization problem, what we want a function to be optimized. So you can think these two problems interchangeably. Satisfaction problem means how you need to satisfy n number of constraints, let's say. In optimization, you say you want to maximize number of constraints to be satisfied. So in this way, these two problems can be think in another way. You can go back and forth between these two problems, typically in the same complexity class. So just wanted to give you the analogy how you can convert from goal satisfaction to optimization to satisfaction problem. For example, if I say a graph coloring problem, right? So in graph coloring problem, what is the main constraint? Main constraint was that there two adjacent nodes should not have the same color. This was the goal satisfaction. You need to put color RGB, let's say, in a tree, and you have to make sure that two colors should not have the two nodes should not have the same color. If I have to convert this as an optimization problem, I'll say there are 10 nodes. We need to maximize we need to maximize cases where two nodes have the different color, or we can say in the reverse way, we need to minimize number of conditions, number of situations where two nodes have the similar condition, two adjacent nodes have similar condition. So this is how this problem has been converted into optimization. It was constraint satisfaction, but we converted into optimization problem. Now coming to the local search or algorithm. What is local search? Local search means you are thinking about nearby only. This is the local search algorithm. For example, someone in, let's say, in a school, and he is doing quite good there, and he is always scoring rank 1, right? Or every time he is securing rank 1 in the class from 5 to, let's say, 10. He think he as a quite superior to his peers, and he think because his world is a very small there, he only knows about the neighbors, he knows about only the classmates, right? He doesn't think about the some peers outside the school. So he is superior, that's true, but in the local region, in the local boundary, he is superior in his school only. So this is kind of a local problem, local search problem. And in case of global search, someone has, let's say, did rank 1 for a problem statement in the whole world. This is a kind of global thing. So here the peers are coming from the whole world. So this is the difference between local search and global search. Global search means you are optimizing a problem, you are searching something globally, but in local search you are just thinking about neighborhood. Am I better than neighborhood or not? Something like that. So it keep track of a single state where I am. I'll move to the my neighbors when, if and only if my objective function would be better, right? And I'll ignore all the paths. This is the local search algorithm, as simple as that. If you see, I am in a state S, I have three neighbors S1 and S2 and S3. I'll go one of them. Which one I should go? Should I go to S2? Okay, I'll go to S2 because my objective function, or whatever the underlying function would be there, it will be much more better. So that is how the local search operates. And what are the advantages? You have to only care about very much little amount of memory. You are not going to consider what is happening in the whole world. You are just thinking about your nearby. You are thinking about your neighbors. What is the current state? And should am I maximum there or not? For example, let's consider a function, a curve, and it has to attain maximum. So what it will do? It is at the some position. Let's say x. It has the two option. It can go further. It can go backward. X plus delta or x minus delta. If we do x plus delta and see what is the objective function f of x plus delta, is it become better than what it was for f of x? If it is so, then it will go there. Otherwise, it will not go. This is the local search algorithm. I'll see the neighbors and see where my objective is becoming better than what it was, right? So, and if it is so, then I'll climb there. I'll switch there. This is how the local search says. So we are only considering the neighbors. If something is at the state S, number of neighbors will be limited, and that is why it is only processing those neighbors. So we can consider it is taking very little amount of memory. Can often find reasonable solution in large or infinite space. That's why it's asymptotically complete. Local search algorithms are right. So please keep this in mind. This is the things you people will it will be like local search. Is it asymptotically complete or not? Yes, it is, because this is the data it has been given that it often finds reasonable solution in large or infinite state space. So as I said, it is searching only in local or the nearby. So can you think it will if it will operate for a large problem, will it be able to find an optimal solution? Yes, it might be. For example, let's consider the same example that we discussed. One boy is there, and from class 5 to 10 he was doing rank 1. After class 10, let's shift it to some other school, and there he got to know other environment. So he is now exploring the world. For example, if x plus delta we did, and we found that objective becomes better than x, then we are at x plus delta. We'll again see what should I do. Should I do x plus double delta to go further in that direction, because my objective function is improving. So if you think whole problem, global thing, locally it's a collection of local stuff, right? So we can assume if it will be operated for infinite state space, it will always find a reasonable solution. It's not sure that always it will find the optimal. It's just saying reasonable solution. If you have to find the maximize a function, it's most likely go very close to maximum number. It may also get the maximum number, but doesn't guarantee that the local search always yield an optimal solution. It may lead to reasonable solution. Why we are calling reasonable? Because it is going very close to maximum value with very little amount of memory. That's why we are calling it as reasonable solution. So this is the property of local search. Now coming to the we talked about constraint satisfaction and optimization, how they are interconnected. Now let's consider something about the pure optimization. What is the optimization problem? All states have an objective function. So if you see in objective function, states means f of x is the objective, and if I'll give the domain values there, whatever the function is taking, it is a kind of state. So all states, if you see, have some objective function. F of x is a function of x1, x2 and x3. This is like 2x plus 1 plus 3x2 plus 4x3, let's say. This is the function. Then all states, whatever the value will give, x1, x2 and x3, some set of values, maybe 0 to 5, 0 to 5, 0 to 10. So at any values of x1, y1 and x2 and x3, it is a state, and if you put that value into function, objective function, you will get some value. So all states have an objective function. Goal is to find a state with the maximum objective function. Our idea is to find out You find out x1, x2, x3 combination where finally your ff is reaching maximum. So this is optimization problem. It is not restricted to maximization only. Maybe you have to find the minimization. So you have to either do maximization or minimization. Both could be possible. But for the given example here, we are talking about, see in bracket also it is written mean as well. So objective can be maximization, can be minimization, both. Doesn't quite fit into path cost or the goal state formulation. Local search can do quite well on these problems. So for few problems, local search do quite good things. So now till now it's clear what is the local search. What are its advantages? Because it is going to reasonable solution. Local search and reasonable solution, you just simulate these two terms and then you will be able to understand. Finally, with the less effort, you are finding some reasonable solution for that. That's good. So there are few problems, as we said, local search can do quite well on these problems. What are those problems? These are the problems we are going to discuss, where local problem is doing quite good with a reasonable amount of time and effort. Hill climbing search. Hill climbing search is a kind of local search algorithm, and we'll discuss how hill climbing search works for 8 queen problem. 8 queen problem is a very famous problem that we already discussed about it. What is the task? A chessboard will be given and 8 queens will be given. Task is to arrange those 8 queens so that they shouldn't attack each other. This is the problem statement. Let me repeat. Problem statement is that you will be given a chessboard and 8 queens, right? And you will be asked to arrange those 8 queens in such a way that they shouldn't attack each other. So if you know chess, you will know how 2 queens attack each other. If they are in the same row, they attack each other. If they are in same column, they attack each other. If they are diagonal, if they are in diagonal, then also they attack each other. So you need to avoid such scenario and put it here. For example, if you see this scenario where 2 queens are attacking each other, here if you see these queens are attacking each other because they are in diagonal, so we cannot put it like that. So we already discussed it as a search problem in our previous lecture. Now how we'll convert it as an optimization problem. Let's try to come up with something how you convert this as optimization problem. So yeah, please think for a moment and then I'll say how we'll convert it as an optimization problem. Yes, so how we'll convert it as a constant satisfaction problem to optimization problem is that you can think of, we need to minimize scenario where 2 queens attack each other. We need to minimize the number of cases where 2 queens attack each other. So for here, this is the heuristic number of pairs of queens that are attacking each other. How many such pairs are there? If in the given board there are 7, and what we are trying to do, we are trying to make it as minimum as possible. If it will be 0, then it is the solution. This is the searching problem where we want to go. But for the optimization problem, you need to minimize the number of queens, pairs attack each other. This is how you are converting a search problem to optimization problem. Please think it deeply how we are finding making it as a optimization problem, and the reverse could also be possible. If you are taking an objective function, you want to maximize this, finally what would be the limit, and that limit you can search it and it can be converted into search algorithm also. So let's discuss what are the state space and other stuffs are with this problem. What are the states? I said the problem would be given a chessboard, given 8 queens, you need to do arrangement of those queens so that they shouldn't attack each other, right? So 8 queens on the board would be given. Any combination of those 8 queens would call state. Because you are, let's say, learning, you are exploring everything, so it can be of any combination on this chessboard, and that combination is a kind of a state. So that's what we are saying. Any combination of 8 queens on the board in some configuration is a state. What a successor function or the neighborhood function means you are in a state S. How will you move? What will be your neighbors, right? How will you define? So we are defining here a move as to move a single queen to another square in the same column. Successor function, if you see, it is saying you can move only one queen, and that too in the same column. So if it is in a column, for example, here this example, if you see, here is our queen. So the successor function will be you can move to this column anywhere, because queen can move in straight line anywhere. So it can go to 13, 15, 13 and above all, and also the below 15, 18, 15, 17, right? So this is how it is saying you can move. The neighborhood function has been defined here. Example of a heuristic function h of n. So how will you define? Finally, if you move it, what you are judging, that is what here heuristic. The number of pairs of queens that are attacking each other. So you move the queen, and now initially it was 17 pairs attacking each other. Is it become better whenever you move the queens? Is it become more less than 17, or it is becoming 17 or more than 17? If it is becoming 17 or more than 17 means your move is not making that much difference. If it is that 17 is being reduced 16 or 15 something, then you can say okay, whatever the move I have taken is quite good. We should go in that direction. So this was the idea about the hill climbing. So try to understand the analogy why you are calling it a hill climbing. You are going for mountaineering, right? When you start mountaineering, you don't see the top peak. Nearby you see the local peak. You try to reach there, and from there you again try to reach another local peak and go like that. This is how it is saying hill climbing. So the concept is similar in local search also. You search in the global, go to the maximum one, and go again and just define your boundary again, and you go search again, right? So let me give you an analogy to explain this one. Yeah, so this is summer season, and I want to go in an area where temperature is very cool, right? So what I'll do, I'll do local thing. So I'll see nearby where the temperature is less. So I can see there is a river place. I'll go there, and that river place also, if I'll explore there, I'll find another spot where the temperature is minimum. So what we have done the local. In one go, I haven't decided I should go to the particular part be near side the river. I decided first I have to go to the river side. So initially here my temperature was 42 degrees C. I went to a river side and the temperature was around 38. There I explored too much and then find out there is a place where the temperature is 37. So this is like a two-step we did. In first local search I went to river, and then from there I did again local search, and then I went to another place there where the temperature is 37 from 38, let's say. So this is how we are doing local search thing. Now let's discuss the algorithm itself, how hill climbing works. So this is the function hill climbing. you are giving problem statement, and finally it will return a state if it is a local maximum. It will give you are giving problem. It will return a state if it is a local maximum. It may be also local minimum. It depends what version you are trying to find out. This is the max version. That's why we are thinking about the maximum. It could also be minimum. What will be the input? Input will be the problem and local variable current node. You give me the current node, you give me the neighbors, I'll return you state if it is the maximum one. So what is happening? We are taking current node where we are. We are seeing what is the objective here, a highest value of the successor of the current one, and we are checking all the neighbors. If value of neighbors less than equals to value of current, if I am seeing my neighbors and their value is less than ours, then what we are doing, we are saying return state current, because no one is greater than me, then I am the only greatest value, right? So I'll return my value and say that nearby is no one is greater, then I can think me as a local maximum. If this if is following, if it is not following, then we are making current node as the neighbors. Because why we chose this statement? Because the if didn't work. If didn't work means there was a neighbor whose value was more than ours, more than current node. Then we said now we are changing the current node and we are making that value to the current node, right? That neighbors we are making is the current node. If you see this one, right? So you got the idea what we are doing. We are in a position P, let's say. We are saying the nearby P1, P2, P3, P4, P5, right? I am seeing, for example, let's say temperature, as I said, I give an example. I want to minimize the temperature. Here is a maximization. It can also be think as a maximization. Let's say comfort is the maximization that I have to do. So I am in the pth position and I have to maximize the comfort in terms of temperature. I have neighbors P1, P2, P3, P4 and P5. I'll see comfort at my point and comfort at the neighbor's point. If I'll see comfort at P1, is it less than me? If it is so, then I say, oh, I'm better, why should I go to that point? I'll see again for P2, is it better than me? Yes, it is. So I'll again be there at my pth position. I see with the P3, no, comfort of P3 is more. Then I'll go to the P3 position. From P, I'll switch to P3. So my current node become P3. From P3 again, I'll see my local hood. And local hood are, let's say, P7, P9 and P3. Am I greater than all those things? Seems like the comfort value at the P3 is always greater than the neighborhood. Then I'll say, okay, I checked in my local neighborhood and it seems like I am I have the greatest value. Then I can treat me as a local maximum and I am returning my state. So this is how hill climbing works. Any doubt, any questions still there? Okay, so it doesn't seem any question we have as this point of time, so we can go further. So there are some problems. I said local search, we are finally sending some values if it is the maximum, and that too in a local region. But there are few problems associated with this algorithm. Could you think of what problem it is would have by seeing the graph also? hill climbing gets stuck in local minimum. You must have read this one. What does that mean? Let's say this is the function of the objective function look like, and you are at this position, this red one. What will happen? You will go your nearby and see, oh no, the objective function decreasing here. You go up here in this side also seeing objective function is decreasing. Then what you can think, I am the maximum one, and you are returning the state. This is the state, is the best state. But if you see the global picture, you can see this is not the maximum one. Here we have the global maximum, and it has stuck with the local maximum. And this is the problem we used to call it as that local search algorithm, particularly this hill climbing, is stuck at the local maximum problem. If this is a scenario, the problem also occur with the flat surface. If function look like something like a flat surface, then what will see, it will do plus delta, function is same. If it will do minus delta, function is same, then it will think, okay, this is the greatest value, this is the largest value that a function can the function can attain, right? Then it will return it as a maximum value. This is the point where function is attaining maximum, but this is not the fact. This is the plateau surface where it is going up and down. It is finding out, no, the value doesn't, increasing, even decreasing. I have a f of x that needs to maximize, let's say only function of x, and this plateau surface f of even giving x as 3 and it is returning value, let's say 9. I am doing x plus delta. I am seeing value at 3, x plus delta is let's say 0.25. So I am seeing the value at 3.5, f of 3.5, it is again 9. So I can see I am doing, okay, going forward doesn't seem to have solution. I'll do reduce the x. I'll do 3 minus 2.25, so which is 2.75. I'll check the function value at 2.75. It is again 9. Okay, then I'll see I went up, I went down, but the value is same. It seems like the function has attained the maximum value, and I'll return the state. This is the problem of plateau surface that occurs, that found, observed in hill climbing problem. Now let's see how much effective is this hill climbing algorithm. In the first slide itself we discussed, they come out with the reasonable solution. They might not come up with the ideal solution, but they'll come up with the reasonable solution. Means your whatever the effort you'll invest to it, you will get some reasonable solution for that. That effort you will get very close to maximum, but might not be maximum. But also your effort is quite reduced, right, compared to when you were trying to find out a global maximum. So this is the stats when you apply hill climbing problem on 8 queens problem. What is the 8 queen problem? A chessboard, 8 queens. I want to arrange the 8 queens in such a way that number of pairs of queen attack each other is minimum. So it is saying 14% times it solves the problem. If you apply hill climbing on 8 queen problem, out of 100, 14 times it will able to solve the problem. It will find out a solution where you will the arrangement of queens, if you see, they will not attack each other. There will not be any pair of queens which attack each other. This is the kind of ideal solution. Only 40% time it is able to do so, but 86% times it is get stuck with the local max minimum. So as we are saying that it has a problem of local minimum. So 86% time out of 100, 14% time it is going to have some solution, and that to the ideal one, but 86% times it is not able to reach to the solution that we are expecting. What solution we are expecting? We are expecting a solution where the chase queens will be arranged in such a way that there will not be a single pair of queen which attack each other, right? So now let's go and see why it is failing 86% of time, and how much effort I have given there. Have I given too much effort, still I failed? Then it is not reasonable problem, right? And for 14% time I got succeed. Have I given too much effort there? And so that we are going to analyze now. So it takes only 4 steps on an average when it succeed. So 14% time, 14 times out of 100, it is finally able to find out the solution, and only in 4 steps given board, it will take only 4 steps to reach to that solution, to reach. And when it get stuck on an average, it takes only 3 steps. So if you can see, the effort is quite less. So that's why we are calling it as a reasonable algorithm. So what are the problems we observe is local maximum. Can you fix it? Can we put some patch or some modification into the algorithm and fix the limitation? Think about it for a moment and then we'll discuss. You can also see this slide and come up with what finally is the random walk. Why we are adding is clear. We are wanting to fixing the local maximum issue, but how we are fixing, just for a moment. So actual term is random walk. What is the random walk? It is saying every time in our previous steps what we are doing, every time we are becoming greedy. We are at the pth position. I was choosing p3 only if my objective function becomes better at p3. Every time I was becoming greedy. If it is not becoming better, I was not choosing the state at all, right? So this is the problem of the greediness, but there might be solution. You go to p2. P2 is obviously not better than where you were, but maybe there is a path exists from p2 to another state which is quite larger than p3 even, which is locally seeming better to you, right? So this is the fix here. If you see, we are also incorporating some randomness. It is saying with p probability, you take what you want to do, take the greedy action. If your objective is becoming better, then you choose the state with the only p probability, let's say 80% time. But 1 minus p probability, 1 minus 0.8, which will be 0.2, means 20% time you also do the select a neighbor with randomness. So I am at the p8 position. There are 3 neighbors, p1, p2, p3. Let's talk about the comfort, same problem. Comfort at p3 is better than comfort at the position I am in currently, there p, right? So there is an option I can go to p3, because for p1 and p2 comfort is not becoming larger, even it is decreasing. Can I choose that? No, it is not. In previous algorithm we are not doing so, but here we are saying no, you should we can also choose p2, because from p2 you can see a path which is going to the optimal value p7, and where the comfort is maximum, right? But if you follow the path of p3, you are not going anywhere. You are reaching finally at the local maximum. The comfort the temperature is 30 degrees C. So it's like you are going to stuck somewhere. So with the same analogy, temperature here it is 42 degree. I want to go to a place where temperature is less. So what I did, I booked car, I went to a place, and I finally reached to a place. So temperature there become 38 degrees C. That's cool. But what I am observing, I am not finding any other place where temperature is becoming less than again 38 degrees C. So I am considering it as local my local maximum. Maximum in the sense comfort maximum, right? But if I have went to another place where temperature might not be 38 degrees C, let's say their temperature is 39 degrees C. But from there a path exists. I'll go to some village from there itself, which is very far, very near to that, and their temperature is only 36 degrees C. So rather than stucking at 38 degrees C, I could have went to 36 degrees C in the village if I have chosen also a bad solution with some probability. And this is why this randomness has been incorporated here. With p probability you take your greedy action, but with 1 minus p probability you take a random neighbor. This was the extra step here, if you see. So how your hill climbing with a random walk algorithm look like. Let's come to the algorithm and discuss how it will be, what changes it will be there, where it will be changes. So changes would be here. This if function will have some change. What change it will have? Will generate a random number between 0 to 1. If it is less than 0.2, then I'll say I'll take a random action. I have option P1, P2, P3. I'll take any one of it by random action, maybe P2. If it is greater than 0.2, I will be what algorithm I was following earlier, the greedy one. If it is, let's say 0.3, it is greater than 0.2, right? Then I'll say I am at the pth position. I'll see where my objective is becoming better. I'll choose the state. So this is where the changes will happen. So here the changes would be, before if there will be another if, and which says if a random number you are generating R is less than, if it is greater than 0.2, then this if will come there. If value of neighbors will be less than the neighbor. Else, after this if statement, there will be else means we have generated a number which is less than 0.2, means we are taking a random action. So then I'll write next state would be random, whatever the states, neighbor states we have, P1, P2, P3. So this is the changes will happen if you are going to incorporate random now. So hope till this point everything is clear. There is another kind of search, local search algorithm, which is known as simulated annealing. What is this? Simulated annealing, by name itself it is some inspired by some annealing stuff. So what is the motivation? Motivation is same as the previous one. You cannot be greedy always. You take also few random actions, some bad move, and explore from itself. Is there any path which is going to global maximum from themselves? So that we also need to do. This is what it is saying. We have some variable called temperature. So by temperature, so as you have heard in the lecture of the professor, he used to say if the temperature is very hot, then you can think you are very unstable, right? You are unstable means you want to reduce the temperature. You are going to take a neighbor which temperature is less, right? Whose temperature is less. Your temperature is reducing finally you are becoming too cool, then you should not take lot of action, because you are thinking you are in a good place, right? So this is what it is happening here. We have some temperature as a variable, let's say 100 degrees C. I am at the some state S. So this is the state, let's say. Oh, that's what a coincidence. The slide number is also 100 and I told just temperature 100. That's nice. So a randomly selected successor of a current node. I have a current node. Next state would be just you generate all the neighbors. This is how the next is there. And see the energy difference. What is the energy at value at the next node minus energy value at the current node. If it is if del is greater than 0, then you make current node as the next node. Why so? Because energy is more there. You are going to a state, from one state to another state. You are at, let's say, current state. You are going to next state if and only if del E is greater than 0, means energy amount is greater there. Here, let's say 25 kilojoule. You will go to another state where the temperature is at least 26, because this difference is greater than 0, right? So if del E greater than 0, then you are making next state as a current state. If it is not so, you are exploring all the states, neighbor state, and finding no, energy nowhere is going to increase. So what we are doing, you are taking current node with some probability, some randomness you are incorporating here. What randomness is there? You are deciding some probability term, maybe 0.2, maybe 0.1, 0.5. But how you are deciding? You are deciding with this del E factor. Whatever the energy difference you have, del E by T means, let's explain. So I am at the 25 kilojoule energy. I checked in neighborhood and didn't find where 26 kilojoule is there. I found few position where 23 kilojoule is there. So what is the energy difference if I'll go there? 25 minus 23, which is 2 kilojoule. So I'll take 2 kilojoule divided by temperature. What is the current temperature? If it is 100, then 2 by 100, right? Then it will be 0.02. You do EQ exponential of 0.02, you will get some number, let's say x. So with that x probability, you take current node as next node. You take current node as a you with next only with the okay, right. So you already computed the next node, so you will select the next node as a current node if it is follows probability terms, right? So let me summarize, you might get confused here. I am at the position P, the energy level is 25 kilojoule. I have 3 neighbors, P1, P2 and P3. Energy level would be, let's say, 26, 29 and 30. So I'll compute del E. I'll see the del E for the state was 29, I just selected, so the difference is 3 kilojoule. I am saying energy difference is greater than 0, means if I'll go there, my energy would increase. Perfect. Then what I'll do, I'll take a switch, I'll do the climb, I'll do the shift, and I'll take this node as a current node. This is one scenario. If you'll not find such scenario, what will happen? You'll then in such scenario, you take, if all 3 states have energy less than 25, let's say, what you will do there, I need to select any of it, either P1, P2 or P3, but I'll select P2, let's say, with some probability. What probability? That probability term will be defined in terms of what is the del E, what is the temperature difference for going there. I know it's good, energy would be reduced, but how much? So that energy difference divided by what is the current temperature, you will get some term, and that you do exponential, then you will get some probability term, let's say 0.16. So you'll take P2 as your current node with 0.26 priority. So this is how you are going there. So you are taking also bait move with some probability, because you didn't have a better solution there. Delhi is always reducing, so you are computed Delhi by T and seeing where the probabilities become high, whether P1, P2 or P3, and then you are choosing that move also. Choosing that move and going there. So we discussed till then two algorithms. One is the hill climbing. What is the problem with the hill climbing? How we fixed it with the random walk. Next we discussed simulated annealing. So it is also like a random walk itself. There we decided priority ourselves, right? P and 1 minus P. Here we're deciding with some dynamic factor, temperature. Now coming to another kind of algorithm, which is again optimization algorithm, genetic algorithms. Oh, what is genetic algorithm? You must have heard the term genetic. So from there itself it has been inspired, and we are going to discuss about this in detail. Yeah. It's also known as evolutionary algorithm. So genetic algorithm uses the direct analogy with the nature behavior. How in nature we have survived. It is just taking the direct analogy of the natural behavior. They work with the population of individual. Population of individual means consider a society and there are 10 people. So this is the population of individuals. There are 10 people, 10 individuals, each representing a possible solution to a given problem. If I'll say meet an appropriate person for, let's say, doing election, then out of 10, one would be appropriate, right? So there could be 10 solution. Those people there, P1 to P10, anyone could be the most appropriate. Not anyone, it depends. Anyone of them would be the most appropriate for doing election. Each individual is assigned a fitness score according to how good a solution to the problem it is. And based on the problem itself, I told you about the election, then I'll say whose background is good for election, who can be a leader, and we'll assign some fitness function to them. I'll assign a fitness function to a person high if he has already organized few camps and led it and have done good work. So I'll give some more score to him compared to other who never involved in people management, right? The highly fit individuals are given opportunity to reproduce. Those person who have the high fitness value, means those who have organized such camps, will be given opportunity to reproduce. Here reproduce terms means they will have a kind of debate. They'll have those kind of debate for, let's say, election agenda by crossbreeding. We'll discuss these terms with what operations are there, but I'm just giving the analogy. So those person will be discussed. What will happen with the discussion? Some good points of person 1 will go to the person 2 and some good points of person 2 will also go to P1, right? So this is how they have reproduced, they have crossed over their information. They produce offspring. Initially the person whose value has high, so P1 to P10, 10%. I assign some score to each of them depending on their previous experience with the people management. I found 2 people very high score, P3 and P7. I put them in a discussion. We have just discussed. They discuss, they do crossover, their points has been exchanged, each of them have taken some good point from other. So P3 person kind of think it has become extra information, P3 dash. Also P7 has some extra information which has become P7 dash. So we got new offspring which is P3 dash and P7 dash, right? They produces offsprings. This is the meaning of that. Before a GA can run, a suitable coding and fitness function is required. So now we'll put these two offsprings, what we are getting, P3 dash and P7 dash into population. So we had 10 population P1 to P10, now we'll have P3 dash and P7 dash. And again do the same operation, selection, crossover, mutation, and finally we'll see where it is converging. So what were the steps? Steps were initialize the population P1 to P10, do selection, which of them have some kind of experience, crossover, put into discussion, mutation means after discussion they also think something, they do in introspection, and finally their agenda become updated. So mutation. Reproduction means, okay, so reproduction is the discussion thing I was talking about. So here, okay, reproduction is finally you have new set of population. So these terms might be confused here, but crossover is something like a debate you are doing and finally exchanging the point of one another. Reproduction means your population size is, it was 10, now it got updated, right? Population have some also other offsprings because they have reproduced. The previous two person P3 and P7 have reproduced, and we have some P3 dash and P7 dash also in the population, right? Hope this analogy makes the things very clear. So in right hand side you can see an image where you have something like you have environment of each individual, there are persons, there are things. You are doing selection from this one who are most likely to go for election, something like that. So these are the animals and go, and I ask them to do reproduce, do debate, I ask them to do mutation introspection, and finally we will have the new generation, and finally this process will go until unless I find the most suitable candidate for election, right? So this is how genetic algorithm works. I'll take a pause for 10-15 seconds to do introspection, and have any question about it. Now let's discuss the important point of the genetic algorithm. Twist on the local search. So genetic algorithm is a kind of modification of local search. Successor here, if you see, is generated by combining two parent states. So in previous states, what we are doing, we are taking an action state at state S, and we are reaching to another state S dash. But here we'll reach to another state by doing crossover over two parents. Two parents will do crossover, and then finally they'll give new offspring. So how new next states or the neighbor states has been generated here in this case, and which is different from in general local search algorithm. So this is what the difference is. A state is represented as a string over a finite alphabet. So it is flexibility, how you represent the state, how you encode the problem, how you represent your population. You start with the k randomly generated state, so you'll have given a set of population. You start with that, you do selection operation, you do crossover, you do mutation, you will have finally the offsprings, you put it into this population. So this is how you are doing, genetic algorithm. What is the evolution function? Evolution function here similar to the same analogy to that fitness function. Higher the values, better the states. If fitness function of a population is high, it means the population is most likely quite close to the optimal state we want. Opposite to the heuristic function. It produces next generation of states by simulated evolution. So this operation we already discussed. Selection. There is a random selection, but there we did some selection criteria based on fitness. Then we did crossover. Then finally mutation. Mutation was random there. Mutation means changing a bit. So you have population look like, let's say 101. Then any position, maybe it's second position, I'm just flipping the bit. So it was 101, it will become 111. So this is how the mutated population will look like. Now let's explain each of the terms involved in the genetic algorithm. There was something called gene. So population is what? Population is collection of genes. Collection of chromosomes. So these all terms are inspired by the natural phenomena. Population, set of chromosomes, and each chromosome comprise of gene. So this is the here it's given. And any of this chromosome, any of this population, this chromosome could be a solution. We need to find out which would be the solution. What is crossover? Crossover means when two chromosomes interact with each other and create a new offspring. This is called crossover. So you can think it as a two parent, P1 and P2 parent, and this is how it represented: A, B, C, D, E, F, G, H, and another one is F, G, H, A, B, D, E, A. If you have to do crossover, means you are making sure that this part, this red box, I'll leave it and take it from else from the same position. So I'm saying this red part I'll not put of myself. These are, let's say, bad genes. So I'll take here, for example, it was okay. So what it is doing so for parent 2 it is FGH. No, I made a mistake. So it is saying the red part are the important. I should take that part. So we are taking FGH. This is important because red part. Again, I have A, B, D, E, but I'm not taking A, B, D. I'm taking from the others. I'm taking from the parent 1, which is B, C, D, E, and red part again from ourselves. It is A. So now new offspring has been created: F, G, H, B, C, D, E, A. So this is how crossover happens, and finally a new offspring is being created or generated. Is it clear? Any comment? Any question? Okay, so we can move further, right? Now coming to the mutation. So before mutation we have this one, whatever we did it after crossover, we had, if you see, we have offspring FGH, BC, DEA. We put it there, FGH, BC, DEA. We'll do mutation. Mutation means masking some of the bit with some other number. Whatever it was initially, I'll just change it. So we decided here we'll do the masking at the third position. Initially it was H, we made it M. And also masking at the last position, which was A, we switched it to N. So now after mutation we have this chromosome where two genes has been changed, H and A, to M and N respectively. So this is the mutation operation. So finally, how the genetic algorithm look like? You just initialize population, that is randomly. What does that mean? It means that if I'll say to find out a solution for a problem P, so you select how problem will be represented by, let's say, 7-bit vectors. So initially those 7-bit vectors combination you can take randomly. So this is what it is. Initialize your population randomly. Determine the fitness of population. Let's say you selected 100 population randomly. Next step, you are determining the fitness for each of these chromosome, each of these population. Until converges, you do these things. You computed fitness function, that's good. If it crosses the fitness value, then they are going in all in these next 4 operations. If not so, they will be discarded. So it is coming from the Darwin theories, means those who will have capability will sustain, other will die. So here we did a fitness function, we calculated, we have some threshold. If crossing, then we'll say they'll go for further operation, otherwise they'll not go in part of algorithm processing. Then let's say out of 100, 88 of them cross the fitness function threshold. They are going to operate for these 4 operations A, B, C, D, E. What it is doing, let's understand. We are choosing 2 parents randomly out of this 88. Let's say chromosome was represented by C1 to C88. So we chose C6 and C36 as parents. They'll do crossover. They'll change their some features and generate new population. C6 and C36 did crossover and finally generated something, a new offspring, new child. Call it as C363, and that 363 we have now C363. Perform mutation on new population. So we have C363. We applied mutation here. Let's change a bit there in mutation. So now C36, there was a bit at the third position 0. I flipped it to 1. Now mutation has been done. You have C363 dash because I changed 1 bit, right? Calculate the fitness function of the new population. So now I will calculate the fitness function of this chromosome, which is C363 dash. It is crossing the limit, whatever the threshold we have. Yes, it is so. Then you put it into the population. This might be a solution. So now we had 88 things. Now it will be 89, right? And we'll operate again these operations. So this is how genetic algorithm works. Now we are going to apply this genetic algorithm for our most popular 8-queen problem. How will you do that? Just think for a moment how you represent the problem. So see how this chessboard has been represented as a string. So we mark each row as 1, 2, 3, 4, 6, 4, 5, 6, 7, 8. So for first one, queen is at what position? Queen is at first position. For second column, queen is at what position? Sixth position. For third, it's 2. For fourth, it's 5. Then we are writing it as a string representation: 1, 6, 2, 5, 7, 7, 4, 8. So this is how this state has been represented in terms of string. That's fine. Now what we'll do, we'll have population like that, states like that, combination of 1 to 8, and this is how it is being represented in initial population. If you see the column A, we'll calculate the fitness function. What does that mean? Fitness function means, given the state, how many queens are not attacking each other, and this is what the number we have got: 31%, 29%, and 26% and 14% are the fitness function. Higher the better, I guess. Yeah, fitness function equals to number of non-attacking pairs. How many non-attacking pairs are there in the state? So they are saying 24 for first one, it's for second one 23, for third one 20, fourth one it's 11. Now if we'll compute 24 by sum of all, 24 plus 23 plus 31 and all, then you will get some percentage, right? You are associating that percentage with that, and let's assume your threshold for selection is 14%. At least 14% time, 40% of the queens should not attack each other. Then they all go for next operation, which is crossover. In crossover, what they are doing, they are changing feature of each other. If you see this first two, 3, 2, 7, I put it's, but I changed 5, 2, 4, 1 to the other one, which is 4, 8, 5, 5, 1, 4, 8, 5, 5, 2. This is how crossover has happened. For similar thing has been done for the second one. We put its property of 2, 4, 7, and it changed other bit 4, 5, 4, 8, 5, 5, 2. I changed it to the same position part from the first one, 5, 2, 4, 1, 1. So this is how crossover has happened. So we have now new states after crossover, right? We'll do mutation. Mutation means changing a particular bit, any bit out of it. So we had for first one 3, 2, 7, 4, 8, 5, 5, 2. Now we decided we'll change one bit, and that too from the third last position. So third last position was 5. I changed it to some random number, so it is becoming 1 here. So after mutation we got 3, 2, 7, 4, 4, 8, 1, 5, 2. What I'll do, I'll take the selection, fitness function, and if it crosses a threshold, I'll put it into the initial population, and then I'll do again this algorithm run there. So finally, in terms of genetic, what it is doing, so it is, if you see what actually crossover is happening, see. So this is a board, in second one another board situation. Finally, what we are doing, we are taking good moves from each other. So we fix the left part, we took the right part from the other one. So if you do plus operation, finally leading to this one, right? So initial part we took it from first chessboard, and afterwards we took it from the another chessboard. Here the effect of jumping to a completely different new part of search space, quite non-local. Let's some major things about genetic algorithm. Genetic algorithm is a variant of stochastic beam search. Stochastic beam search was also K state start. It starts with the K state, right? Here it's similar to the population. We are starting with the K population, N population, whatever you call it as. There are few pros and cons of genetic algorithm. Let's discuss those pros and cons. The first one is the random exploration can find a solution that local search cannot. So here we have lot of randomness. Where we have randomness? We have randomness in crossover, we have randomness in mutation, and it is saying it may lead to solve the limitation of local search, which is stucking at local optimum. Appealing connection to the human evolution. It is quite similar to how humans, interact and those things. So it is appealing connection with the human evolution, how human has been, evolved. Neural networks, genetic algorithms are the metaphors. So you will read about the neural network. So neural network and the genetic algorithm, how they have been compared. They are kind of analogy. They are the metaphors of each other. So they have particularly strong foundational background. This is the meaning. What are the negative points? What are the cons? What are the limitations of genetic algorithm? Large number of tunable parameter. We have very large number of tunable parameter. What are those? What should be selection fitness threshold? What should be the position from where we should do crossover? What would be the mutation point? And all these are so many tunable parameters. This is the problem. Lack of good empirical study comparing to the simple methods. So there is lack of empirical study that compares how it is doing for simpler compared to simpler methods. Useful in some set of problems but not convincing evidence. It is doing quite good, but we don't have a proof for that the GAs are better than hill climbing without random restart in general. So these are the pros and cons. Now we are going to discuss few questions and then we'll have the session about that, right? So till then you just have this see about once, and I have any question, let me know. Any question further about this discussion point, or we can go and discuss assignment problems related to this problem, this point, genetic local search and all. Let's go there. The first question is, which of the following algorithm asymptotically complete? We discussed in the slide itself whether it's random sampling of states, local beam search, random walk, or hill climbing with the random tree start. Which one would be asymptotically complete? Asymptotically complete means if problem size increases, then it will have the solution. This is the meaning of asymptotically correct. So these all three things, random sampling with the states, random walk, and hill climbing with the random start, will have the asymptotically complete solution. We already saw there for random walk it is asymptotically correct, hill climbing with the random start is also asymptotically correct, because if problem size increases you will have the randomness property here, and that is a kind of giving you the boost that finally it will have some solution lead to state. Genetic algorithms are said to jump from one hill to another hill. Which of the following is responsible for such behavior? So in hill climbing you have read it used to go from one state to another state. In genetic algorithm, what is the synonymous term for that one? Whether it's a mutation, crossover, fitness, or natural selection, which one would be the most appropriate? Think for a moment and I'll discuss. So here in genetic algorithm, what is the analogous term for going from one state to another? So in hill climb, what was happening? Going from one state to another state. What is this? It is like a going from one to neighbor one, right? So in genetic algorithm, how we go from one to neighbor state, how new population has been created is the crossover. So that's why the answer would be crossover. Another question is, Mona is doing a hill climbing. Mona is a girl and she is doing hill climbing. She observed that her procedure often gets stuck in a plateaus. Which of the following addition to the procedure would help to recommend? So C is getting stuck in local minima or maxima, whatever the problem, expects. What suggestion will give? Allow indefinite sideways, allow sideways move but up to a certain limit, keep a taboo list of recently visited nodes. Taboo list means just tracking whatever we have already visited, so that you already said, okay, I have visited there, why should I go there? Otherwise you will fall in loop that it kind of discard. For example, A to B I went, and from B it is saying go to A, but if I have in my list I already visited to A, then you can discard the loop. You said no, I visited A, and from A to again I'll come to B, so that loop would be discarded. Perform BFS to find out the next node with the better objective function when the state is stuck in a plateau. Perform a BFS to find the next node with a better objective function when the state is stuck in the plateau. So you'll say, okay, if you have stuck in a plateau, what you do the BFS and find out the successors and take the one with the better objective function. What will suggest out of this 4? Just think for a moment and then we'll discuss what to do with the right answer. Allow indefinite. So what would be the answer? Answer would be, you ask her, give the suggestion that allow sideways, but up to some certain limit, right? So that you're able to recall whether it's a loop, then you can discard those scenario. Keep a taboo list. As I said, it helps you in going in a loop. Perform BFS to find out the next node with a better objective function when the state is stuck in a plateau. You'll perform the BFS and see what are the successor and take one with a better objective function. Next question is hill climbing, sometimes called which of this? Needy local search, heuristic local search, greedy local search, and optimal local search, because it grabs a good neighbor's state without thinking ahead of the where it has to go. Yeah, it's only think about the local stuff. So what you call it as needy, heuristic, or the greedy? Obviously greedy local search would be the answer. Next question, which of the following problems can be modeled as CSP, constraint satisfaction problem? 8-page problem, 8-pin problem, map calling problem. So first slide was itself, right? Every constraint satisfaction problem can be treated as an objective function, and these all can be treated as, can be modeled as CSP because they are the search problem. So all of them would be the answer. Yep. So this next question is, backtracking is associated with what? Last in first out, first in first out, recursion, and both last in first out. So backtracking means you are you went to A to B, B to C, and C to D, and from D you are saying there is no path. So you are doing a backtracking from D to C, C to B, and B to A. So what is happening here? What it is last in first out, because you are popping out D, then C, then E. So last where node which has in, it is going outside. And this is the same scenario with the recursion. If you call f of 3 and it is called f of 4, let's say, for example, you are calling factorial function. So factorial is like if you are calling factorial of n, which is n into factorial of n minus 1. So what is happening? It is going again like a backward direction only, right? So you finally compute f of 1 and then multiply with so f of 4, if you have to calculate, which is 4 into f of 3, you are not going to compute f of 3. You are again saying 4 into f of 3 would be 3 into f of 2. Again you are making it smaller, 3 into f of 2 as a 3 into 2 into f of 1, and finally you are computing f of 1 which is 1, and then you are going there, right? So it is also same as backtracking. So recursion and both are last in first out would be the answer. Constraint satisfaction problem on finite problem typically solved using form of search algorithm, heuristic algorithm, greedy search algorithm, all of them mentioned. So it already discussed they can go back and forth, right? CSP and search. So the answer would be all of them mentioned. Which of the following is or are about local search algorithms? So read this statement, very important question. Which of following statement is or are true about local search algorithms? They are guaranteed to always terminate with a correct solution. Is it so? No, it's not. Who said? There is no such proof. They are highly memory efficient compared to the tree graph search algorithm. Yes, it is so, because we said it is only search local by and consider only those things. They can only solve a certain variety of optimization functions. Not exactly. They can solve lot of they don't make any assumption on the structure of optimization function. Yes, so they don't make any assumption on the structure of the optimization. So answer to be they are highly memory efficient and they don't make any assumption on these things. This question is this: someone wishes to solve 8 problem using hill climbing problem with the random restart. It is known that the probability of a successful run of the hill climb algorithm on this problem is 0.14. On average, how many restarts should C expect? Right. So this is the question. So for this probability, if you see what does that mean, it is saying it is known that probability of a successful run on a hill climbing algorithm on this problem is 0.14. What does that mean? It means only probability that you will reach the solution is 0.4. In order to make it as a 1, what you will do, you will run it many times. So it is asking how many times you are doing random restart. So for idea is that it is currently 0.14. If you want to make it for one step, it is 0.4. How many steps it will be close to 1? So it will be 1 by 0.14, which is very close to 7. So answer will be 7 here. Hill climbing algorithm terminates in which of the following condition? Hill climbing algorithm is there, and when it terminates, stopping criteria met, global mean and max is achieved, no neighbor has a higher value. All of these. Hill climbing algorithm terminates in which of the following conditions? When it terminates, it is the question here. No neighbor has the higher value. This is the definition of hill climbing. Now I'll go to another state if it has a more value. If all of the neighbors should have not any of them have the more than me, then I'm not going to make a switch, right? So answer would be no neighbor has a higher value. Next question is which of the following algorithm keep track of k state instead of just one? Hill climbing search, local beam search, stochastic hill climbing search, random restart hill climbing search. There are 4 options and they're asking which of the following algorithm keep track of k state instead of just one. So you remember what we said, even in genetic we did so, but here genetic is not the option. So which of these have start with the k states rather than one? Which is local beam search. Here we used to do a k number of solution, right? Local search algorithms are not systematic. That's true, they don't do systematic, just see the neighbors and switch. The main pros include which are the following. Okay, so local search has a problem, that's cool, but is there any also benefit with that? So what is the benefit? The benefit is the less memory, because it is seeing only the local neighborhood and they are very small in number, right? Less memory, and also I forgot this search solution in the big and it has always a kind of solution in big infinite space, because they are asymptotically complete algorithm. Now next question, if you see, this is the population given, how population look like? Binary string 0 1 0. There are 4 population 0 1 1 0 1 1 1 triple 0 0 1 triple 0 1 double 0 1 1. So we are calculating now fitness function. So fitness function look like something like that. F of x summation of f of x, where f of x is x square. Means fitness function of a population would be first convert into decimal, square it and divide it by sum of square for all other values. So this is the problem here. If you see, we had this binary in decimal to represent 13. F of x square will be 169. For all we calculate this one. Then what would be the fitness function for the population? For let's say first one, it will be 169 by sum of all. So 169 by 169 plus 576 plus 64 plus 361. So it has asked the for this population, then it will be 576 by 169 plus 576 plus 64 plus 361, which is coming around 0.492. So this is the fitness value finally we are getting, because it helps whether if it is greater than some threshold, then only it will go for other operations such as crossover mutation, right? Otherwise it will be discarded. Now coming to the next question. Any question, any doubt for this one? Okay, seems no. What are the differences between simulated annealing and genetic algorithms? So there are 4 statements. What are the differences between simulated annealing and genetic algorithms? Genetic algorithm, genetic GA for genetic algorithm maintains candidate solutions while SA doesn't. So in genetic algorithm, yes, we used to have multiple candidate rather than like a simulated annealing. SA is used to minimization problem while GA is used for maximization problem. No, this is not true. They can both use it for minimization, maximization. SA has no parameters to set, where GA requires you to set multiple parameters such as crossover rate. That's also not true. In simulated annealing, you have also few parameters such as temperature and all. GA will always convert to an optimal solution faster than SA on any given problem. No, that's not the fact. So only the truth about all this 4-1 is GA maintains a multiple candidate solution while SA doesn't. Now there is a worksheet that the problem I want to discuss one is this one. Right, hope my screen is visible. Yes, it is so. So this is here. Suppose a genetic algorithm uses chromosomes of X. This is the form A, B, C, D, E, F, G, H with a fixed length of 8 genes, and A, B, C, D are the genes. Each gene can be any digit between 0 to 9. Here it can be anything from 0 to 9. Let's assume the fitness function is defined as A plus B minus C plus D plus E plus F minus G plus H. This is how it is being defined. And let the initial population consist of the 4 individuals. So this is how population we have given. This is given here. X1 is equal to look like this one. So A, B, C, D, E, F, G is now, and they said they can belong from 0 to n, 0 to 9, and they have given finally you the set of 4 population, which is looking like this. Now what we are going to do, we are going to evaluate the fitness function, and fitness function same as this. So A plus B means sum the first 2 bits, 6 plus 5 minus other 2 bit C plus D. That's what we are doing, C plus D, and then again sum of the next 2 bit. Sum of next 2 bit is 3 5, deduction of next 2 bit 3 and 2. Finally we have 9, right? So f of x1, fitness function for x1 chromosome is 9. Similarly we calculate for other as well. So what would be the order of their fitness would be x2 is higher compared to any other, 23, then x1 9, then x3 minus xn, and then x4. This is the order of fitness score. Now we are going to do crossover operation. So how we are going to do crossover? So if you see how fitness function x2 was looking like, 871266601. We wrote it there, 871. We took the most fittest function x2 and x1. x2 is this one and x1 is this one. We are doing a crossover at some point at the fourth position. So what we'll do, we'll put initial fourth position as ours, 8712, and I'll take other fourth position from the others, which is 3532. I took it here if you see. So now offspring 1 is 8712, my property, my zine, and 3532 from other x1, right? Similarly for x1, if you do, first 4 bit would be r 6451 and another 4 bit 6601 will take from first one. So our next offspring will look like this. Cross the second and third fitness individual using the 2 point. This was the 1 point crossover because we decided we'll do crossover from the fourth position. There is also 2 point crossover. So we are doing crossover over, if you see 2 points here, second and third, fourth, fifth, sixth and seventh position. Third and seventh position we are doing here. So we'll put first two from ours, 6 5. We change it now to the others, which is 9221, and remaining 2 bits will take ours only, 3 2. So this is a kind of 2-bit 2 point crossover. So we'll have O3 and O4, another offspring. Now what we'll do mutation. So here mutation is just flipping a bit. Flipping here, we decided we'll flip these positions. We flipped 8 7, we flipped 8 to 2, we flipped 2 to some number, and like that we flipped it. Now we'll have this new population. What is the new? We started with the fourth population, O1 to O4, let's say. We have offspring now, O5 and O6, right? Now we'll calculate a fitness function, and finally our fitness function would look like something like that. With the same function we calculate f of x is equals to a plus b minus c plus d plus e plus f minus g plus h. This is the how. So overall, if you see the what had happened, the fitness function has improved. Why so? We have now better set of pool of population which is most likely to go to solution. So why it is saying we have better one, let's calculate it. So 9 plus 23, 31, minus 16, which is 15, minus 19, minus 4. So overall, if you do, it is minus 4. Now in this scenario, let's do it. 15 plus 17, which is 32, 32 minus 2, 30, 30 minus 5, 25, 25 plus 13, which would be 38, 38 minus 6, which will be 32. So obviously fitness function has improved. So we can see by doing crossover mutation, we have now better pull-ups population, and from that if we'll do workout, we'll get a state which is attaining of the objective function. So this is how it is working like that, right?